Hello everyone. So this video is all about the variants of Swern oxidation. So I will suggest you to watch the previous video, which is Swern oxidation, the link of which you will get in the description box, or you can click top right corner. Right now the link is appearing. Okay, because if you do not have the prior knowledge of Swern oxidation, it will be difficult to understand the variance reactions of this Swern oxidation. So let's start. As you can see here we have total 1, 2, 3, 4, 5, 6, total 6 variations of Swern oxidation. So in Swern oxidation, which you can see in the below, here 1 degree or 2 degree alcohol is our substrate in presence of reagent DMSO combined with oxalyl chloride, that is the first step, and the second step we use base. And what is our product? Aldehyde or ketone. Now when we are talking about the variants of Swern oxidation, here also we are using DMSO. Only in one oxidation, one procedure, you can see here we have used DMS, which is dimethyl sulfide, right? So DMSO is common, and here what is the common point is that in all the cases we will make some activated DMSO, because once the DMSO is activated, the attack of this oxygen which is present in our substrate alcohol, that can easily attack. Okay, so activated DMSO, that will be formed. So one by one we will see what is the mechanism for all these variants of Swern oxidation. So here we have the first one, which is Pfitzner-Moffatt oxidation. So in this case the reagent with DMSO that we are using is DCC in presence of acidic medium. So DCC structure you can see here, NN dicyclohexyl carbodiamide, which in short it is drawn in this way. So CY means cyclohexyl group. Now in presence of acidic medium, this one of these nitrogen that will be protonated. Once it is protonated, the DMSO, this molecule is DMSO. So this oxygen, now it will attack at this carbon. Nitrogen will be neutral. Now you can see this is basically the activated DMSO. Once it is formed, now the oxygen's lone pair that is in our substrate, that can easily attack the sulfur. Right? So now sulfur oxygen bond will be formed. Once this sulfur oxygen bond is formed, sulfur is now neutral, and this nitrogen which you can see here, this CN double bond, this can capture this hydrogen. Once this hydrogen is captured, this sulfur oxygen bond, that will be broken. Once it is broken, the fate of this DCC, now it is removed in this molecule in this form, and we have obtained S-ylide. Once S-ylide is formed, rest of the mechanism, the story is same that we have already seen in case of Swern oxidation, that you can see in the previous video. So what happens here? The hydrogen which is present here, that is taken by this CH2 minus, and that is a carbon, and finally this carbon hydrogen bond is broken. In this position there will be CO double bond. So finally we will obtain our carbonyl compound, right? And the fate of this part is, that is DMSO, now it will be converted to DMS, that is dimethyl sulfide. So rest of the mechanism I have not written here because that is same. So here we are not using any base. DMSO is obviously there, but for its activation we have used DCC, and there is acidic medium. You can find the reference details. The next reagent is Albright Goldman oxidation. Again DMSO is present, and we have taken AC2, acetic anhydride. So this is our DMSO molecule, and this AC2O, that will be attacked, one of this carbonyl group that will be attacked by this oxygen. So what will happen? This there will be negative charge generation over this oxygen. So this is our activated DMSO, because DMSO is already activated by this molecule, and this lone pair over this oxygen that is in our alcohol, that will attack here. Once this attack is occurring, sulfur oxygen bond will be formed, and next what we will do, this OH, because oxygen there is total 3 bonds, so it is protonated, right? Now acetic acid molecule will be removed. How? See this negative charge, if it is making CO double bond, there will be negative charge over this oxygen which can take this hydrogen, and as a result there will be net removal of acetic acid. Finally you will be left with this type of molecule. Now this hydrogen which is present here, if it is making, that is CH bond broken, C double bond O is formed. Now sulfur oxygen bond broken, there is negative charge over this oxygen which can take this H, and again there is acetic acid removal, right? and the fate of this part is, that is the fate of DMSO, is dimethyl sulfide, Me2S. This is our final product. So only in this mechanism you can see there is no sulfur halide formation, but activated DMSO is there, so that alcohol can attack easily. The next reaction is Parikh-Doering oxidation. So here for activation we are using SO3 with pyridine. Now in SO3, this DMSO molecule, if it is attacking here, one of the sulfur oxygen bond is broken and there is negative charge generation. This is our activated DMSO, right? Now the alcohol will attack, that is this oxygen will attack this sulfur, and if this SO bond is broken from this total part, see, it is nothing but sulfate ion, right? SO4 2 minus. So this sulfate ion along with the pyridine that is present with this SO3, though it is not written here, but you can see SO3 dot pyridine. So this pyridine and sulfate, it can it will be removed in this way. So you can see the ion pair. So this part we have obtained from the alcohol, that is our substrate, and DMSO, and here we have positive charge, and in the second bracket, if you see second part, that is the species within this third bracket, here 2 negative charge, 1 positive. That means 1 positive charge within the first species, and the second species within bracket there is negative charge. So this is as if the ion pair. So that is the role of pyridine, you can say. And finally, as you can see, ET3N is present in the medium, so it will help to generate this sulfur halide by capturing this hydrogen. And rest of the mechanism, as we know, this negative charge, it will be taken this hydrogen, CH bond will be broken, this bond will be broken, and there will be CO double bond. That is our final product. Next is Parikh oxidation, and here it is not DMSO, it is NCS. It is DMS, and for its activation we are using N-chlorosuccinimide. This is N-chlorosuccinimide. Right? So this DMS, dimethyl sulfide, what it will do, this sulfur, it will take this chlorine, NCl bond will be broken, there will be negative charge over nitrogen. Now this negative charge, again it will attack this sulfur, and there will be activated DMS formation, not DMS, so it is activated DMS, and chlorine is removed as chloride. Now once this activated DMSO, next thing is obviously attack by this lone pair over oxygen which is present in our substrate, right? And once this is this N-S bond will be broken, this H, it is now with this N negative. Ultimately this is the fate of NCS, and this is our as ET3N is present, so finally you can generate the light, that is negative charge will be generated at this position, and we get our final molecule, right? The next reagent is Onodera reagent. Here we do not have any specific name, see here, if you look at this paper, phosphorus pentoxide DMSO triethylamine. So convenient procedure for oxidation of alcohol to ketone and anti, and there is no specific name reaction, but by using this Onodera reagent, if formation of chlorinated side product is a problem. So in some of the previous method you have seen, just take Swern oxidation itself, there we have used oxalyl chloride, so chlorinated side product, and then another previous reaction also you have seen chlorinated side product, that is the NCS, N-chlorosuccinimide, that we have taken. So if we do not want to use chlorinated reagent or side product generation problem, if we want to remove, we can use this method. So here Onodera reagent is, though it is written in this way, DMSO P2O5 ET3N, but Onodera reagent is solution of P4O10 in DMSO. So this is basically the dimeric form. So here one particular example, as you can see from this book, you can see this reaction. Here this COH that is converted to C double bond O, and rest of the part there is no change. So here we have taken this Onodera reagent, right? So here also the activation of a DMSO you can expect in a similar way. So this is our DMSO molecule, and P2O5, as we know that oxygen phosphorus bond is very strong. So as a result, what will happen, this oxygen, it can attack this phosphorus, this P double bond O is broken, right? Now once this attack is occurring, sulfur is still positively charged, oxygen phosphorus bond is formed, and rest of the part there is no change. Now you can say this is as if the activated DMSO, and when you have your substrate which is alcohol, this substrate it can attack this sulfur, and this sulfur oxygen bond that will be broken. So once it is so, now you are getting finally OS, right, and it is still that is positive, sorry, it is positive charge, right. So in this way, finally ET3N is there, negative charge generation is possible at this position, and rest of the mechanism as we know, right. Now the final procedure is a Liu procedure. Here for activation of DMSO we will take PDCP, which is phenyl dichlorophosphate. So this PDCP molecule here again the negative charge over DMSO, it will be attacking this phosphorus, chlorine will be removed, that is chloride will be removed, we have obtained the activated DMSO. And the next thing is obviously the attack by the alcohol. So when alcohol will attack here, there will be a removal of this part, that is OS bond is formed, and this part will be removed, and once this OS bond is formed, ET3N is in presence of ET3N, there is a negative charge generation possible, and as we know sulfur halide that will be formed, and rest of the mechanism just like the Swern oxidation. Okay, so that's all in this video. But so many variations of Swern oxidation you have seen. So even in exam, if you are not seeing directly the reagent of Swern oxidation, which is a combination of DMSO, oxalyl chloride, then some base, then also don't just panic. You have to understand that there may be some variation, right? So if you know the mechanism, so even if some unknown reagent is there, just try to understand the mechanism, because it is not always directly the name reaction will be given, that we cannot expect always. So that is why all these variations, it is important for us to know. So I think it will this video will help you not just Swern oxidation but also the other variations. Thank you for your precious time.